Okay, so we've got day 3 today. And after we do our day 3, we're going to cover maybe some information on our quiz and that. But the order of magnitude of a number is the integer portion of that number, common logarithm. Okay, two numbers have the same order of magnitude if the integer portion of their common logarithms are the same. Okay, and that integer portion would be our power of 10. The order of magnitude is used to make approximate comparisons of like quantities. A kilometer is 3 orders of magnitude longer than a meter. Okay, and for those people who haven't run cross country or skied cross country skiing, we're talking about, they always say, hey, we got a lot of K in today. And that's all about 1,000 meters, 1K. Okay. And if you look at the Berkey, which is, I don't know, what is that? A lot of K. It's 33 miles. What is that? That's like, it's like it's like 33 miles though. I think it's a 50K. It's a 50K. It's 33 miles. Okay. But I know I say okay, but we're talking about K, so we're fine with that. But you gotta be thinking as we go through. $1's 2 orders of magnitude greater than a penny. Okay, so a penny is 1 cent, but $1 is 100 cents, so it's 2 orders bigger. A horse weighs 400 kilograms, is 4 orders of magnitude heavier than a mouse weighing 40 grams. Okay. Yeah. Okay. New York City with 8 million people is 6 orders of magnitude bigger than Earmuff Junction with a population of 8. Okay. I don't know what you got to do to be a city, and maybe somebody just doesn't like say, hey, that they're in our city, but you have a group that's on a ranch, and we're going to call it Earmuff Junction, and we're going to have 8 people there. So it's kind of interesting. Go out and buy yourself a land and have a family of 8, and you have a city, I guess. All right. So this is one of my examples I love. But exploration, comparing scientific notation and common logarithms. Using a calculator, you can compute the log of 4 to the 10th, the log of 4 to the 10 squared, the log of 4 times 10 to the 3rd, the log of 4 times 10 to the 10th. I'm gonna save you some time on that. We're not going to compute it. What do you think is happening with it? As far as the decimal number, the integer. Because it's going to return an integer value, right? The log of 4, the natural log of 4, which is going to be something less than 1, okay, between 0 and 1, times, in this case, 1, times, in this case, 2. I mean, like added to it, I should say. So why don't we just pull it out for a second, just to like think about it, because you guys are kind of like staring it off, and I kind of want you kind of hypothesizing what might go on. So check that out. Pull out your calculator. Pull out a calculator if you've got it. I've got plenty back here if you need one. Okay, we'll probably be using some base change stuff, so it might be something you want to do. And all I want you to do is just pop in, hey, the common log of 4 times 10. Okay, and find what that value is. Okay, well, that's 1.60205. Well, that means the common log of 4 is 0.6, because the common log of 10 is just 1. Does that make sense? Yes or no? Because based on what we've done, this should be the log of 4 plus the log of 10. This one should be the log of 4 plus the log of 10 squared. Okay, so we should be able to notice that the first one was 1.602. The next one's going to be 2 plus 0.602, so it's 2.602 and so forth. This can be 3 plus 0.602. Are you okay with what's going on with these? As far as I'm looking at the logarithms and what we've done before with our properties, because this is 4 times 100, this is 4 times 1,000, but it still means the log of 4 plus the log of 100, the log of 4 plus the log of 1,000, the log of 4 plus the log of 10,000. So that's where we're getting our values. Are you okay with that? Yes, no, maybe. So what's the pattern in integer parts of these numbers? The integer is the power of 10. Okay, does that make sense? Because 4 is achieved by being a partial or fraction of a value because it's less than 10, so it should be between 0 and 1 someplace. What's the pattern of the decimal parts? Decimal parts stay the same because that's the log of 4. Okay. How many orders of magnitude is 4 times 10 to the 10th, then 4 times 10 to the 1st. And so it's 9 orders of magnitude larger. Does that make sense? Yes or no? Ladies, shh. Are there questions about the order of magnitudes at all and what that means? Yes, no, maybe. Okay. Now, orders of magnitude are used in comparing noise, severity of earthquakes, and acidity. Okay. I go back and forth on this based on what I just talked to you about. How many times more severe was the 2001 earthquake in Gakar, I'm pronouncing this right, Gakar, India, which was on the Richter scale at 7.9, then the 1999 quake in Athens, Greece of 5.9. How much more severe was it? What did we just find out? What did we talk about at the beginning of class? Should be 7.9 minus 5.9, right? Because we're talking about how much worse it should be. Ultimately, the Richter scale difference of 2 corresponds to an amplitude ratio of the 2 powers of 10 of this. So I'm just looking at the earthquake in India was 100 times more severe than that in Athens because of their difference on the Richter scale. But I'm going to show you where they come up with that value on the right side. So here's what they were talking about when we first did this. Okay, so they want us to find the difference of the two. Okay, and that kind of goes right into the difference of the two values here. If I take this value and find their difference, because the Richter scale is based on this information here for those measurements. Okay, and I know that it's already 7.9 minus 5.9, according to what they gave me in my problem. And I'm looking at this Richter scale comparison. This is my Richter scale. It's the log of A over T, where A is the amplitude in micrometers of the vertical ground motion at a receiving station. And have you guys talked about receiving stations? You probably have seen something, whether it's volcanic or something around the San Andreas Fault. They have these receiving stations, and that's why they have the wave coming in, and they actually read these things. The period of the seismic wave in seconds. The weakening of the seismic wave is beta, or your B wave with increasing distance from the epicenter. Kind of like if you shook, a rope or something, and it's just how it goes through, how it dissipates, or throw a pebble into the water, and you see bigger wave, and then it dissipates out. Okay, because it doesn't go on forever unless it's really big, and then still doesn't go on forever because of the medium it's running in. But the idea of this is that they were going to talk about subtracting out a beta, because I was looking at this, and we can say, well, these logs can be grouped together, and we can have them be 7.9 minus 5.9, because our beta at the time, we could say it was 0. And we could finish this out by talking about our powers here, and that's still 2. And I got a kick out of this when I went through this, and the t's would knock each other out, so it's a over 1 or a over 2, and this is still inside my fraction. And for those folks that are wondering where the t went, remember a over 1 t times t over, so the t's would cancel out. That's how I was able to go one step to the next. And then the final steps here, we were talking about this being raised to the 10th power. If I put this in the power of 10 here, that would be 100. But the idea of that, these calculations show the A1 to A2 ratio of severity. And when we were making a test, the instructors wanted to do this with you. And I was like, why? All they have to do is find the difference between the two quakes and know that it's a power of 10. Does that make sense? This steps through and says, hey, these are powers of 10. You've got to make sure you recognize, if you have earthquake and it's Richter scale, you just take 7.9, subtract 5.9, it's 2. But it's a power of 10. So remember, it's a common log. So they're asking, what's the severity? 10 to the second power is the difference in the severity of the quake. And that's why I was able to talk about it that way. We didn't have to go through this explanation to find that. Does that make sense? I just wanted to make sure you saw why we'd worry about the Richter scale, where we found the differences, and what was going to go on. And remember, this B and this B, they're just 0 because they knocked each other out. Okay? So that's how I got here. And I'm still finding what's going on as I go through my problem. But the ultimate answer here is this. And we could have answered it before we even started doing the computations. You okay with the Richter scale difference? And you can do that in anything. When they start talking about it, if you've experienced an earthquake, there aren't too many in the Midwest. It's possible, but we don't have as many. So if you're out in California and you experience an earthquake, and then they tell you what the score is, normally it's like 2 to 4 pretty basic earthquakes, that they'll come out and you'll have quite often. But as soon as you start getting up in the 6, the 7, the 8, wow, okay, it's like taking a Scrabble board and just shaking the crap out of the thing when you get up, if you're in the middle of losing, okay, your Scrabble game. Anybody seen a Scrabble board? You guys know what I'm talking about? It's kind of like Words With Friends with wood tiles. Okay, all right. So this next one, in chemistry, the acidity. Acidity is a pH thing. It's also powers of 10. Okay, is measured by a concentration of hydrogen ions, in the solution in moles per liter, and the hydrogen ion concentration is written as an H+. Because such concentrations usually involve negative powers of 10, negative orders of magnitude are used to compare acidity levels. The measure of acidity used is pH, the opposite of the common log of the hydrogen ion concentration. Okay, so that's the opposite of our hydrogen ion concentration is the opposite of that. So when I'm looking at this, if I'm talking about vinegar, the opposite of the hydrogen ion concentration in vinegar is supposed to be 2.4. And they told me that right there. That's why I was able to do it. Okay. Now, I can find the moles per liter on this. If I just look at this and I take this to the 10th power, and all I did is here at this point, I divided by -1 on both sides, and I'm taking this to the 10th power. Okay. And when I do this with a common log, when I have this situation, it's my answer to that is there. And that's why I can do that. This is raising 10 to the -2.4 power. Well, put that in your calculator. 10 to the -2.4 power. And I'm able to find about 3.98 times 10 to the -3 moles per liter. Okay, that's my concentration. Are you okay with the work, the algebra work with the logs? Yes or no? Because it's the same stuff that I do when I'm graphing a logarithmic function without a calculator. Now, the other thing was the pH is 8.4 for baking soda. Remember, the opposite of the log of hydrogen, to find that concentration is 8.9. So, divide by -1, multiply by -1 to both sides, I get to that spot. I raise them both. Remember that I can do this. I can make them both exponents with a base 10, because if they were exponents with my base 10s, I would set them equal to each other. They are equal to each other, so the value as exponents, with 10 being the base, will still be equal. Why do I do it? So I can drop out the log. Okay? It allows me to have the log drop out based on properties. So now I know the hydrogen concentration is equal to 10 to the negative 8.4 power. Okay? I put that in my calculator. Right? Pop it in. I get my moles per liter again. But this one's my moles per liter is 3.98 times 10 to the negative 9th. Now, just looking at my moles per liter, what's the order of magnitude difference? What's the difference between 10 to the negative 9th power versus 10 to the negative 3rd power? You okay with 6 orders of magnitude difference? You okay with that? Yes or no? Okay, so how many times greater is the hydrogen concentration? The hydrogen concentration. And all I needed to do, that's the vinegar and the baking soda between the two. And I'm just dividing them. Negative 2.4 minus negative 8.4. It's 10 to the 6th difference. Okay, so by how many orders of magnitude do the concentrations differ? Hydrogen ion concentration of the vinegar is 6 orders of magnitude greater than that of baking soda. Exactly the difference of their pH. Okay, so when people ask about these things, if you know it's a pH scale and it's a logarithmic base 10 scale, all you have to do is find the difference of the pH. Okay, pH is kind of important because it allows us to open our eyes underwater when it's really nice, which is 7.4 to 7.6 without any irritation. Okay, I mean, it's kind of nice because the pH of your eyes is like a 7.4 to 7.6. And then, are you guys familiar with acids and bases? More one way or the other. It's more acidic, more basic, but both are more irritating to your eyes if you open them up, and to your skin for that matter. Okay. Questions about this? And it really comes down to, we're talking about orders of magnitude. So although we did all this, what it really comes down to is the difference of the pH scale, the difference of the Richter scale. Okay? Pretty quick questions all of a sudden, aren't they? Now, this next one is a cooling, Newton's law of cooling. An object has been heated with and will cool to a temperature of the medium in which it is placed. Okay, it's heated up, it's pulled out of the microwave, it's set on the counter. Okay, or a very similar object is heated up, it's pulled out of the microwave, it's set out on your deck and it's 14 below. Which one's going to cool faster? The one out on the deck or the one on the counter inside? Well, it depends. If you're at my house, it'll probably be the one on the counter inside is going to cool faster. Okay, but the one on the deck should cool faster because the medium around it is colder to start with, right? So you would like theorize that between the two, that the one out on the deck would cool faster. When we're looking at this, we have a temperature T of the object at time T, T of T. Okay, temperature T of the object at time T can be modeled at the temperature the object is at the time it is, and then the temperature of the medium around it. Okay, which means the air around it, the water around it. Okay, for this cooling. So T of M, this temperature of surrounding medium. T naught is the initial temperature of the object, whatever it might be. Okay. So it kind of makes you think that the medium temperature is really having a lot to do with this. This model assumes that the surrounding medium, although taking heat from the object, essentially maintains a constant temperature. So it's not like I'm going to take a boiling hot pan of water out and I slip it into a box that's just barely bigger than that, because it should heat up the box more if I closed it than the room would. So they're assuming that the medium, that whatever is cooling, is much larger, okay, than what is being cooled. So if we look at a problem on this, hard-boiled egg at temperature 96 degrees Celsius is placed in 16 degrees Celsius water to cool. Okay, by the way, anybody boil eggs, hard-boiled eggs? Okay, pretty good, right? I always boil my eggs, my water. I put my eggs in and set the timer for 15 minutes. Okay, 15 minutes later, they're awesome, but I always put them in nice, cold, icy cold water so I can peel them easier, right? Otherwise, if I let them sit there, just like the craggly looking eggs, it looks like potholes in springtime on the Minnesota roads. So, roads, you know, as you roll down the road, you feel those potholes. Okay, hard-boiled egg at temperature 96 degrees Celsius, okay, is placed at 16 degrees Celsius water to cool. Now, the 16 degrees is my medium, okay, that I'm cooling in, my cooling area. The 96 is my initial temperature of my object. Now, 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. Now, what we need to be aware of when we're doing this problem, I kind of color-coded it a little bit to make our lives easier. Okay, in this first one, we're given the temperature of the egg after a certain amount of time, 4 minutes. Okay, and the reason they give us this is they want us to find a K constant. So we have information that we can use. We have our medium, 16 degrees Celsius, and we pop those in. We got to find our K because it's negative, the E's raised to the negative KT, and our time here in minutes is T, which is 4 when we did our first one and became 45 degrees. So I'm going to use that information to help me find my K. So I'm going to pop that in. And I got 96, my T naught is 96 minus 16, and I quickly did it when I was writing it out, and maybe, you know, I looked at it later today, and I was like, you know, I probably should have showed you that it was 96 minus 16, but I'm trusting y'all can go 96 minus 16 and come up with 80. So this is where I've got all my numbers, and I got my K. At this point, I'm solving for K. So I'm going to subtract 16, which should give me a 29 is equal to 80, e to the negative k times 4 power. And now I'm going to divide by 80 and take the natural log of both sides so I can get that k fourth on the main line of the equation. Remember, I'm using properties of the natural log. If I take the natural log of e, whatever e is raised to, whatever that power is, that's what my answer will be. So that drops my negative 4k. So I'm going to take the natural log of 29 divided by 80, and that whole thing should be inside parentheses. I want to make sure that that's clear. That's my argument inside my natural log. Be careful about your notation because it's really easy to like slip that natural log of 29 divided by just 80. That's a whole different number completely. Okay, now I'm going to divide this by negative 4, and I'm able to get that K is 0.2537. Okay, now it goes on in my calculator, and because it's a constant that's going to be used in the equation to help me find other information, I'm going to put it in my calculator. I'm going to store it. I actually stored it in my calculator as K. Okay, do you guys know how to do that using your alpha key to store in your calculator? Because I'm going to store that as K in my calculator. So now when I plug it in my function, okay, I can actually use it to help me find what they asked me to. So I've got that K value, and I want to be emphasize that's K in calc. I just put K in my calculator so I could quickly do the computation and I didn't have to slow myself down and have fat fingeritis because I pushed the wrong buttons for my K value. And now they're asking me to pretty much run the same thing, except they're asking me here to find my time T. Okay, I'm going to find my time T when it will be 20 degrees. So now in time T, I'm no longer concerned with 45. I'm concerned with 20. But 96 is the same, 16 is the same. Okay, we're assuming that's what's going to happen when I pull it out. Now, Those are the differences. Now this time, I did the solve to help me find K on the left in blue. I got you started in green. I want you to do almost, it's a very similar solve. It's not exactly the same, to find your T. You're finding time T. How many minutes it will take for the egg to cool down to 20 degrees Celsius. Or perhaps cool enough to peel without feeling like you have to treat it like a hot potato. Okay? So, go ahead and find your T. By the way, this is our last example. We are not doing the re-expression stuff. Now again, just like we did before, we're going to subtract 16, so I got 4, and I'm going to divide by 80. So I got 1/20th really if I reduce. So I'm going to take the natural log of 1/20th, and I've got that negative 0.2537. Remember, that is a value in my calculator. That's why I got that dot, dot, dot there that I saved from over here where I said, you know, hey, sort in your calculator. And now I'm going to divide my natural log by that t value, and I'm going to find 11.809. Okay? So what that means to me, remember, when we got a word problem, we got to describe, explain what we're doing, and on this one, it's here someplace, the temperature of the egg will be 20 degrees Celsius after 11.809 minutes. Remember, in this class, when we're doing decimal answers, we need to carry it out to 3 decimal places. And that transfers to 11 minutes 49 seconds. So in 11 minutes and 49 seconds, it'll be 20 degrees Celsius, as long as all the information is 96 degrees Celsius when it came out. It's 16 degrees Celsius, water, my medium and my water. If my water is colder, we would expect it to cool faster. Okay? If my water was warmer, it would cool slower. So keep that in mind when we're gauging these. Are there any questions? Now remember, we had to use the original information they provided to help us find our K constant. All right, for that medium. Notice how I said that, for that medium. Because although this relationship, the Newton's cooling law relationship works, K changes with the different mediums in situations that we have to make that predictability happen. That K has got to be found on something that we kind of have predetermined. We already know some temperatures, the start and end point, and then we can find our K, and then we can extend that information to others, you know, other times to find out when those temperatures would be. We won't be doing the extension in the next ones just because it's directly related to re-expression. It's not unimportant. It's something that we're not testing on, and you won't use re-expression in calc until, I mean, I don't even know if you do re-expression in calc, so I'm not going to worry about it. But reading it is kind of an interesting side as we go. So we have our assignment here for day 3, number 45, 49, 50, 61 to 63. But before we get into it, I want to take 6 minutes and review graphing logs by hand, okay, without a calculator. Because I've got some people that did pretty decent with it. I got some people that really relied on their calculator. when I went through the quiz, and it's something that I need you to be much better than we currently are. So that's why we're doing it again. Let's look at this. The first one is, I've got a logarithm, and this isn't in your notes. I just kind of made these up before you guys walked in today, after I, ruminated on that test. And I want you guys to know a couple properties of this. If I have a logarithm base between 0 and 1, I can have the reciprocal of that base, because basically it's easier for me to work with a base 4 than a base 0.25. And how I can make the change, according to properties, this is the same equation. It's the same relationship. And one of the things that's really nice about the calculators, specifically your color calculator, is if you put in two relationships that should be the same, the first one will graph, and then if it's the identical relationship, that color calculator will color over it and change the color of the graph. That's how you can check to make sure you haven't screwed up. But I had some folks not doing these real well and really relying on the calculator, and the calculator was giving you some wrong information, or at least you interpreted it incorrectly, one of the two. When you're doing this, you're going to solve for x, much like what we just did solving for t and k, except they're variables. So I'm going to take and get that negative to the other side. I don't care how you do it, multiply or divide. But I got negative y equals here, and I got log base 4 x minus 1. Because it's log base 4, that 1-to-1 idea, those are 4s. So this is going to be 4 to the negative 1 power, and this is x minus 1. I don't even know why I put parentheses around it, but I've got x minus 1. If I was going to graph this by hand, I would look for values of y that work for this. And what's nice about this is I come up with my y values, I evaluate, and I'll have my x values. I have defined x in terms of y. In this relationship, I made x dependent on my choices of y. So I'm going to choose y. I'm going to choose some nice y's as far as I'm concerned. I'm going to put in negative 2, negative 1, 0, 1, and 2. Those are the numbers I'm going to choose for my y. And I'm going to plug them in and evaluate. I got negative 2. Well, opposite of negative 2 is 2. So 4 squared, 16, plus 1 is 17. Opposite of 1, so I got 1, it's 4, plus 1 is 5. I got 0, I should have 2. I'll put in 1, it's 1/4 plus 1, so it's 1.25. I put in 2, it's 1/8, okay? So that's 0.125, so it's 1.125. 1.125, somebody has to actually write it. And I can graph that. Now, a couple side notes on this problem. I'm not putting it on a graph, so you may or may not recognize some things, but this is going to tell me what my asymptote is. What's my asymptote? My vertical one. X equals 1, right? So my vertical asymptote is x equal 1. My domain. Okay, if you want to kind of quick graph and think about it, I've got x equal 1 as my asymptote going on here. I've got 17, negative 2. I got 5, negative 1. I got 2, 0. I've got 1.25, 1, and I got 1.252. This graph is going to come down like this and go off. Okay, so from my domain goes from 1 to infinity. In my range, folks, I got a lot of people who are looking at their calculator and they're not paying attention to the fact that the calculator is going to stop right about there, because your calculator will not give you that vertical line as it approaches your asymptote. It'll just stop. And I got people estimating that. It was like, well, that looks like, 3 high to a negative infinity. It's not. All real numbers. We're talking about the fact it goes from negative infinity to infinity. It's not about what the calculator's telling you. It's limited in what it can give you. You have to know those things. Are there questions about what I did in 1? And I was able to generate a list quite quickly. I need you guys to do the same in 2. Okay? First thing is solve for x. Okay? Give it a try. First thing is solve for x. If you got questions about this, this is manipulation with logarithms. It's also part of a manipulation with e, using exponential functions. Keep in mind, anything I'm doing in notes, I'm expecting you to be able to do on a test. And anything I do in notes without a calculator, I expect you to do on a test without a calculator. And Chapter 3 has a no calculator version, not version, portion of the test, and a calculator portion of the test. So again, one thing at a time. Y plus 5 is equal to log base 2 of x minus 1. Are you okay with that first thing? Get everything whittled away. Now we're going to put them in the position of being exponents to base 2 because our logarithm is base 2. Okay? So now this is 2 y plus 5 power equals x minus 1 to the y plus 5 power plus 1 for our x. And now I can pick my x and y's. And folks, I'm doing it based on this relationship. Okay? I picked my y's based on that relationship and that one alone. First of all, most of the time I'm going to be looking at a graph that's 10 by 10. Okay? 10 out, 10 up. Okay? And that's what I'm going to be dealing with. I'm not going to have a 40 graph in my first quadrant. So when I'm looking at this, I'm thinking, well, if I put in 0, which would be really cool, y 0, that's 2 to the 5th power. That's 32. Add 1, it's 33. Okay, I'm just going to kind of emphasize that. That's 0 plus 5, it's 5. 2 to the 5th power is 32. I've got 33. Okay, I put in negative 1. That's 4. 2 to the 4th power. Well, that's kind of nice. 16 plus 1, 17. I put in negative 2. Well, that's 2 to the 3rd power. That's 8 plus 1, it's 9. I put in negative 3. That's 2. 2 squared is 4 plus 1 is 5. I put in negative 4. Well, that's 2 to the 1st power. It's 2 plus 1 is 3. I put in negative 5, which is really slick because, negative 5 plus 5 is 0. And 2 to the 0 power is 1, so 1 plus 1 is 2. I quickly just generate a list of coordinates I can graph now based on how I solved that relationship, and I just totally did it calculator free. And it works the same. Now, you cannot graph this relationship and expect it to be the same as your other because we use this to help us find our x values. Okay? But I can promise you put these in a list and you put the L1 and L2, you put your list out there and you put your actual function to be graphed in your calculator to check whether you're doing it correctly or not, it works. Okay? And I want to encourage you to check. If you've made a mistake, in all honesty, it's a sign error in this stuff. Okay? So be careful about it. But I just generated a set of values, calculator free, that we can graph quickly for a log function. And I did it log base too. I didn't even do a change of base formula or anything with it. I just took it the way it was. Now, my asymptote, completely decided right there. Okay, that decides my asymptote. That's where it's going to go. Okay, and it's x equal 1. My domain. Okay, if you want, I'm way out at 33 and 0. I go to 17, I go negative 1, but It's still going to be going up. It goes from 1 to infinity, just like the other one. Crazy. That really, I should probably change those numbers just for fun. And then my range, negative infinity to infinity. Okay, even though your calculator will return a funky looking graph, it's a negative infinity to infinity for my range. Are you okay with that? Now, I do want you to give thought on something like that. We're not going to do it together today, but I want you to think about it because I'm going to open tomorrow with that before we go on to our 3-6 stuff. Okay? Thank you for your time today. Thank you for your patience.